con lo cual ahora pasamos ya pues, a un viejo conocido de este escenario, también miembro que nos ayuda mucho en el grupo profesional alimentario, Mario Martínez, el profesor titular, investigador consolidado en el área de tecnología de alimentos de la Universidad de Valladolid, pero también profesor asociado en el Departamento de Ciencia de los Alimentos en la Universidad de Aarhus y adjunto en el Whistle Center for Carbohydrate Research. Mario realmente tiene un equipo y un programa de investigación muy centrados en la ciencia y la tecnología de biopolímeros, que nos va a hablar de ellos en su charla, que se titula Crafting and Integrating Next Gen Plant Polysaccharide Ingredients, con lo cual creo que por ahí van a ir los tiros. Y sus estudios, para que sepáis, han sido presentados en más de 150 congresos científicos, menciones en medios de comunicación de países como Estados Unidos, Canadá, Dinamarca, bueno, donde queráis casi, lo podéis encontrar.
Gracias, Miguel Ángel. ¿Me oís bien? No, está apagado, ¿verdad?
Sí.
¿Ahora me oís bien? No. Sí, ahora sí, ahora mejor.
Ahora.
Sí, era culpa mía, Gracias por la amable presentación y, bueno, para mí es un placer. Gracias también al comité organizador, el comité científico, por invitarme a compartir un poco con vosotros lo que hemos estado haciendo últimamente, que siempre se agradece, ¿no? Contaros un poco lo que hacemos. La presentación la voy a hacer en inglés por una sencilla razón. Tengo todas las diapositivas en inglés y si hablo en español y leo en inglés me voy a acabar confundiendo. Entonces, bueno, voy a pasar, I'm going to change to English to make it more flowable. So I would like to start the presentation by talking about what drives our post-meal responses. So while genes play a role, it turns out that what we eat is the real game changer. And this is important. Let's take a look, for example, at that chart over there. It's a very large-scale, high-resolution clinical study with a lot of participants. And you can see there that what we eat and the meal composition was the main factor affecting, in this case, postprandial glucose response. This is very important because this means that we are not prisoners of our genes. This means that we can change our responses, our physiological responses with our food. This is already something very important to consider. This also means that we can formulate population-wide nutrition strategies for preventing chronic disease. This is important. But in order to make this work, it's important to enhance the precision of our understanding about the effect of the food structures on physiological response. Let's take apple as an example. Something relatively simple, but not that simple. In apple, we have very complex cell wall structure, the plant cell wall, and also we have a very broad profile, for example, of plant secondary metabolites. Another example, for example, is the starch. Starch is a very complex supramolecular structure with with a lot of complexity in the level of structure. So there is still potential, but we need to understand the effect of all these structures on the metabolic response. But it's not all about eating apples sometimes, because the way we are exposed to these structures is affected by many different factors, defined as dietary exposomes. That could, for example, mean that our personal preferences. Some of you may not like apples. I will never purchase apples because you just don't like it. Or because of our eating patterns, or because of our behavioral patterns of lifestyle. So it could be a very interesting and elegant strategy to enhance our exposure to these structures by integrating these structures into other food matrices. That could be very interesting. It is challenging, yes, as I will show you after, but it could be an interesting way to enhance our reach to these structures and hence improve the chances for these structures to improve our metabolic response. In terms of dietary fiber, this is a very good example. Dietary fiber is a very complex matrix at different hierarchical structures. But and you all know that dietary fiber, it can support of gut microbiome, and this is something very interesting. But in order for this, there is a couple of considerations in terms of dietary fiber. First of all, we want the dietary fiber to have enhanced. We want our bodies to tolerate them better and to feel better for that. And for that, we need a slow fermentation rate. And this can be attained with certain structures. For example, by having those fibers being partially insoluble or partially aggregated, or by, for example, having complex structures in the fiber, complex molecular structures. The second consideration is that the different microbiome will respond differently to fibers. So in order to have a consistent results among all of us after dietary fiber exposure, it could also be interesting to enhance competitivity towards another group of bacteria. And this competitivity can also be attained, for example, by having these supramolecular aggregates on insoluble structures, because we will force bacteria, for example, to have this sort of cellulosome-like appendages that are needed to open up these structures, or, for example, by having complex polysaccharides in which we will have a broad array of glycosidic linkages, and therefore we force the bacteria to have a lot of enzymes to be able to metabolize this bacteria. With that, we will be able perhaps to obtain a consistent metabolic response or positive effects across individuals. One elegant workaround about this idea is just mixing fibers. And in fact, it's a good strategy. You just mix fibers, and it has been reported that if we mix fibers or if we have different fibers, it will perform better than just including an individual fiber into that. And there is more to it in terms of complexity, as if it wasn't complex enough, is that during processing, we have some secondary metabolites in the inner part of the cells, and sometimes we process these materials. We can press them when we're going to make, for example, juice, and then we press them, cold pressing, well, anything we do, or even during chewing. And then we will have all those secondary metabolites also interacting with the dietary fiber, adding an additional layer of complexity. Now, the interesting thing is that there are some fruit and vegetable byproducts that bring all of these structural factors into the table. They are a combination of fibers, they have insoluble material, jet fermentable, we have a broad complexity of glycosidic linkages, and then we have glued polyphenols with untapped metabolic activity. And yet, we're throwing it on the garbage, we're disposing of it improperly. So I just wanted to tell you with this the enormous potential that some of the byproducts, fruit and vegetable byproducts in this case, have, and we're still discarding them. So the first thing that I want to talk about is, okay, we wanted to understand what are those polyphenols that will be glued to these dietary fibers during conventional processing? And we use apple as an example because it's very abundant and it's a rather simple matrix. So this is why we were studying apple. So firstly, we wanted to see, okay, how much polyphenols will we retain in those byproducts, and what is the profile? What is the chemical profile of those polyphenols? We wanted to do that by really understanding the whole picture of the metabolome, and for that we use high-resolution mass spectrometry so that we don't miss any of the compound that we have there. Because some of them there is no standard, so we really need to identify those compounds by using these techniques. Then we were making use ourselves, but using a pilot scale protocol, really resembling what could be done in the private industry. And then by using these techniques, we were able to investigate or to get a profile at both subclass level, that means the effect of the distribution of polyphenols by core structures, namely 6 mostly polyphenol subclasses that are, as an example, phenolic acids, flavonols, etc. But also we are able to dive further and go into individual level and really understand what are the discrete molecular structures of the polyphenols that will be glued to the plant cell wall. So the first thing that we observe is that not all the polyphenols remain bound to the pomace equally. They are mostly oligomeric flavanols and flavonols. Those are the ones that will be mostly retained in the pomace. Whereas the others, they are retained not a little bit, but not that much. They go to the juice. This is mostly what you will drink in the juice product. So hence, we will end up with pomaces being a very rich reservoir of flavonols and oligomeric flavanols, which could be something interesting already to see. And then we were also, because we are able to go at individual level of all the polyphenols, and we have a lot of structures that we are investigating at the same time, we can establish structured binding relationships. So we observe that those polyphenols that are of larger molecular weight, slightly more hydrophobic, and we have a larger count of hydrogen groups, those ones will be mostly retained in the pomace, and they're expected to be in the pomace. So now the next question is, okay, what happens if we eat this pomace? What happens with those polyphenols if we eat this pomace? Will they reach the colon? Will they be released in the mouth, in the stomach, etc.? So then in order to obtain understanding, we had to develop I would say an elegant in vitro digestion system, starting from the standardized InfoGest 2.0 model, where we were, mostly what we did, we were simulating physically the absorption process, which at the same time allowed us to have cleaner digesters to be able to run mass spectrometry on them. Mostly, this method consisted on removing insoluble material, so those polyphenols will not be released anyway, and also having here a centrifugal filtration with a 1,000 kilodalton cutoff, mostly resolving what could be absorbed in the epithelium. We were doing a lot of work in terms of digestion. We were also investigating the effect of the mucosal digestion. And for that, we were adding scraps from the rat intestine because they are rich in alpha and beta glycosidases, which are the ones that digest polyphenols. But those enzymes are not included in the standardized digestion models. So we also wanted to see what happens in the presence of these enzymes, which are the ones that we have in our body. And we observed something interesting. Well, of course, we needed this enzyme. This is what is called RISE, rat small intestine extract. And you can see here the generation of the aglycons. This is after the digestion of the polyphenol. The polyphenol, we have the glycosylated polyphenol, the polyphenol part, the glucose part. So after the digestion, we release the aglycon. You can see that in the presence of the plant cell wall material, the access of these enzymes towards the digestion of the polyphenols is decreased. So we already are having an effect. So it has already an effect on alpha and beta glycosidases as well. So this covers another enzyme activities. For example, we just published this paper last week. We discovered that certain polyphenols glycosylated to a glucose moiety via ester can be digested in the lumen, which hasn't been reported before. And also we were testing other things. I just wanted to say with this is that we invested a lot of work and effort on trying to develop in vitro digestion models to understand what is going on with the polyphenols in the matrix, and in this case in the pomace. So these are the digestograms. We were grouping them by subgroups, but you can see that when we have pomace, so here this is the juice is the blue line and the pomace is the red line. So you can see that the bioaccessibility is rather low for all the polyphenol subgroups. So it's very low. So this is also interesting because this interaction that we saw before during juice making, they are strong enough to result in minimal bioaccessibility of these polyphenols. So they will not be released as we digest them. They will be mostly pushed towards the colon. Could that be something good or not? Well, I will show you now. Also wanted to understand if there was any association, any structural parameters from the polyphenol that could explain what is going on. And in the case of apple, it did. We could see that different groups, for example, here we can see the dehydroxychalcones that behave very differently compared to others. So mostly we could predict based on the polyphenol core structure, we can predict what's going to happen when we have a plant cell wall material glued to it. But in the case of the pomace, there was no association. Because the pomace, for whatever reason, we were producing the pomace, we were drying that before running the digestions, the plant cell wall will collapse. There is some supramolecular changes occurring there, and those changes will overrun the effects of the polyphenol structure. So this means that either all the polyphenols will be retained similarly, or they will not, but they were retained. So this means that the polyphenol molecular structure has a lower role in that. So now the next question is how are these structures, which is mostly plant cell walls impregnated with polyphenols, how will this affect the gut microbiota? Because we already saw that they will be mostly reaching the colon. And this is difficult to study because we are working with very complex systems. We are working with a plant cell wall material. We are working with real polyphenol profiles, mostly glycosylated. There is no standards, or they are very expensive. At least I cannot afford those. So how can we study this in a meaningful way? So for that, what we did is we developed the first thing in terms of the plant cell wall material. We we built our own plant cell walls using a bottom-up approach. So what we did is we took advantage of the cellulose biogenesis by Gluconobacter silinus, which secretes cellulose bundles. And we did that in a medium already containing pectin and xyloglucan. So by doing so, what we are doing is we are creating an analog of the plant cell wall that is rather similar to real plant cell walls in terms of chemistry, but also structure. And then we were doing some compositional studies to verify that it was really plant cell wall analogs really resembling a real plant cell wall. In terms of the polyphenols, what we did is we were getting the extract and then we were soaking this plant cell wall material in the extract. And then we were observing which polyphenols were retained, and we could also see that it resembled what we were observing in the real plant cell wall. So here we have a very nice model because it is like POMAS, but with everything controlled in terms of compositions and structure. And then we can compare these two. We can compare the plant cell wall with no polyphenols bound and the plant cell wall with the polyphenols bound. And this is very interesting because then we can see if those polyphenols, this additional layer of structural complexity, will have a prebiotic effect or not, which is what is the situation of all of these fruit and vegetable byproducts. And then we conducted a batch fermentation study, in vitro batch fermentation study with 5 individuals. We were comparing the cell wall with no polyphenols, the cell wall with polyphenols, and then a control with no plant cell wall and anything. So the first thing is to try to understand the metabolomics during gut fermentation, and hence here we have to compare all the time with the plant cell wall without the polyphenols, because many of the polyphenols in the feces could be coming from the background diet. So we are comparing all the time to really see if the polyphenols, to really track the polyphenols that are coming from the structures, from the treatment. And we observe, for example, and this is interesting, that within the first 5 hours of the treatment, a lot of polyphenols were really metabolized. So here we can conclude that there was a rapid microbial catabolism of those polyphenols during fermentation. So this is interesting because those polyphenols, they resisted digestion because they are glued, they are entrapped, but they didn't resist fermentation. The bacteria were able to open up the structure, access them, and metabolize them. And I think this is interesting. And there was inter-individual differences. It depended a little bit on the microbial baseline of each individual. In terms of short-chain fatty acids that Clarissa mentioned before this morning, we could also observe that a reduction in formic acid, which is good, and an increase in acetic acid production. So those polyphenols being glued there are doing something. They are, well, I would say, enhancing the potential of the dietary fiber as a prebiotic ingredient. And again, we are throwing it away. It's a very premium prebiotic ingredient that we are throwing away. In terms of microbial community dynamics, there was no significant changes in relative abundance, but delving a little bit more into it and investigating donor by donor, we could see something interesting. Well, most microbial families were affected by having the presence of the fiber, but there were others that were more affected, other species, and depending on the donor, they were more affected by the presence of the polyphenols, which I think is quite interesting. Now, as I mentioned before, we have a premium fiber, amazing, fantastic fiber that we are throwing away. Now, can we put it into a bread product? So what's going to happen? How the dough will react, how the bread will react? Well, it reacts very bad, as you can see there. This is the hardness. So when we include these fibers into the bread system, it will be terrible. It will be very bad. So how can we solve this? Let's go to the other extreme. Let's talk about a fiber that does work in a bread system, such as psyllium husk, for example. Here we were making breads with different levels of wheat flour replacement by psyllium, up to 10%. So here we could see by doing that, we were able to increase significantly the dehydration level. So we have much more water in the system, okay? The volume, the specific volume was rather similar, as you can see there. And besides needing a much more dough hydration, we will also observe those that had much greater elastic response as measured with this creep recovery testing, which we believe it is because of the high propensity of these arabinose islands to form hydrogen bonding with whatever they have around. Now, we wanted to see, to investigate a little bit the water dynamics of the system. And we do that by using proton relaxometry because we wanted to identify, okay, we have more water, but where is this water? Is this water in the granules? Or is this water in the intergranular space? Because if it is in the intergranular space, it will be plasticizing all the polymers that we have there, including gluten. So we will have a better dough structure and crumb structure at the end. So here you can see this peak, this area over here. This area in the low field time domain NMR corresponds to intergranular water. So we could see that by adding psyllium, this is a semi-logarithmic scale, so this area is much greater, as you can see there. We have more water in that space, plasticizing the polymers. During storage, obviously, that water goes down because there is a water loss. So how is this water loss? Well, here you can see here, for example, in the area, it goes down because everything is staling. There is migration of moisture at the microscopic scale from crumb to crust. But there is also redistribution of water between all the macropolymers that we have there. But it doesn't matter because what matters is that at the end of the storage period and almost during the entire storage period, we have all the polymers better plasticized. So even during storage, so even after 6 days or 7 days, we could have gluten more plasticized because we have the water there. So this is a great fiber. You can see here even the hardness evolution. So this is fantastic. This is the control, hardness development, and this is, well, an example of a 10% psyllium. So the effects are dramatic. This also results in, because we needed much more moisture to hydrate the dough, so we will have much more moisture throughout the entire system. So yeah, this is what I mentioned before about plasticizing gluten. Because if we plasticize gluten, we ensure that it will be in a rubbery state and not in a brittle state. It means that it will still be able to perform as an elastic, viscoelastic unit. And I think this is quite interesting. Now, this is a fiber that works. Okay, POMAS, completely the opposite to this. Okay, and also in terms of crumb resiliency and cohesiveness, everything improved. This fiber is fantastic, I must say. We were very, very surprised. And in this study, we wanted to understand why it's working so well. This was the meaning of the study. And when we at POMAS, is terrible. So what do we do? What do we do now? Because it's fantastic. I hope I convince you that apple POMAS is fantastic in terms of nutritional properties. Since we understand biopolymer and water dynamics, we wanted to see, okay, let's do something. Let's try to co-add arabinose islands with these POMAS or pectin. Let's see if, and then we have two different structures, ionic polysaccharide and a neutral one. And let's see what happens. So this is what happened. Here you can see the breads. So this is adding POMAS and then co-formulating with psyllium or pectin, we regain the volume again. Now let's go here with the hardness. See this terrible effect? It was completely counteracted for two reasons. In the case of, and then obviously we studied the water dynamics. In the case of the psyllium, we confirm that by adding psyllium, we keep all the intergranular network better plasticized, even in the presence of POMAS. And in the case of pectin, in terms of water dynamics, is a thief. It steals water from the other polymers. It's not good. But since we needed so much water to hydrate the dough, that water persisted. So then we had to consider a different length scale, the mechanisms resulting in these positive effects, both in the better texture. So now what happens with all the polyphenols? Because we are adding apple POMAS, it's very rich in polyphenols. And we doubled the content of polyphenols in the dough just by replacing 5% of wheat flour by POMAS. We doubled the content of polyphenols. But as you know, baking or bread making will result in polyphenol degradation, or could result in polyphenol degradation. So the question is, how is polyphenol degradation going when we add POMAS into a bread system? And what happens when we co-formulate with other polysaccharides? So this is what we observed. So here, this is a Holm-Sidak a chart where it means that anything differentiating from zero means either degradation or higher recovery. Higher recovery means that not only they weren't degraded, but the recovery after baking, it was even greater. Okay? So we can see that in the case of the orange one, many of these values are above zero, meaning degradation. So we are losing some of the polyphenols as a consequence of the normal bread baking process, which is something that we were expecting. Some other polyphenols are solid as a rock. It's not that we are losing all the polyphenols. No. Some of them are solid, but others are not. Others will be degraded. So what happens when we co-formulate with these compounds? Well, here you can see that we supported, especially with the pectin, supported the degradation of these polyphenols. So not only we're unlocking the possibility by co-formulating with polymers, unlocking the possibility to upcycle apple pomace as a prebiotic ingredient, but also we are protecting the inherent polyphenols initially present in the pomace. And these are the families that were mostly protected, which are highly bioactive. So at the individual level, we wanted to see is, okay, but can we, is this affected by the polyphenol structure? So by the polyphenol core structure, because we always want to try to see effects of polyphenol core structures, because we can have all these subclasses and see what happens to them. But see that the standard deviation became much greater. It means that each polyphenol, even within the same subclass, are behaving differently, to the point that we weren't able to explain these effects based on the core polyphenol structure. We had to delve further into discrete molecular structures. But in any case, I think it was interesting, and pectin performed better at protecting polyphenols and resulting in breads with a greater bioaccessibility of those polyphenols. And in terms of starch, I also wanted to see, because I mentioned that the starch is also a complex structure, this is another strategy that we are working with. This is mostly the food making process, where we have a lot of structure at different less scales, and food processing is mostly the art of destructuring and restructuring again, especially in the case of making bread. So some of the strategies that we want to pursue in terms of resulting in a starch that is more slowly digestible or resistant to digestion and then becomes dietary fiber is creating or preserving this dense molecular network that resists gelatinization and digestion, or introducing in the chemical structure some bulky groups that impede enzymes to digest this starch. So these are the famous resistant starch type 4 that probably you are familiar with them. These starches are mostly produced by esterifying starch with different donors, and then you have this RS4. But here we are trying to, and the problem is that in order for that esterification to occur, you need a lot of sodium hydroxide. So there is a lot of environmental problems, environmental concerns. So we develop a novel chemical route to completely avoid the use of any catalyst. Well, this is the reaction. I don't want to talk much about that, but mostly here what we were doing, we were trying to identify eutectic solvents that when put together, well, and obviously that are mostly biosafe and natural and all of that, that they have a melting point before the reaction temperature, that they are thermally stable, they resist the reaction temperature, that they solubilize starch, because this is one of the main problems, or open up the starch, and that they don't destroy starch, because there are some eutectic mixtures that make the starch disappear like magic. So we found this combination of 1:1 molar ratio choline chloride and urea that were able to create all this very nice system that acted as a very nice chaotropic solvent, because so we made the starch to be at least susceptible for any modification. Then we conducted the reaction, and we were able to we created a mathematical model, and we were able to replicate any degree of substitution that we wanted. If we wanted low degree of substitution or very high degree of substitution. So we were able to esterify all viable OH groups if this is what we wanted. Very high atom economy. This means that most of the starch coming into the reaction came out as a product. So very high atom economy. And yes, there was some molecular weight degradation, but still the end product has a higher molecular weight of 1 million Dalton, which still is a very massively large molecule. We optimize the reaction so that there is no formation of side products, and then what we have at the end is really just esterified starch. Is this important? Well, this is just from a picture from another study that was published by other authors in the Cell House and Microbe. And here you can see, for example, the effect of some of these resistant starch type 4 on the gut microbiome, and they are they show that they are not digestible, but that they are fermented and they can result in different metabolic benefits. But I wanted for you to see is that these two starches that are rather the same is RS4, both of them. In this case, they were mostly D-starch phosphate, both of them. One of them coming from tapioca, the other one coming from potato. But you can see that even small changes in the structure of these rather similar starches resulted in massive differences in their prebiotic effect. In fact, in the potato RS4, they weren't digested, but they weren't even fermented. They didn't result in any changes in the gut microbiota. So I just wanted to illustrate with this paper the importance of understanding structure and to understand the complexity and the effect of structure on the metabolic responses. So with this, there is a whole world of complexity in food systems waiting to be explored and harnessed for tailored nutrition. We can create an additional layer of nutritional relevant chemistry and structure to foods. And here I just showed two examples by harnessing the natural impregnation of cell walls during conventional juice making, or by creating novel catalyst-free reactions. I saw the importance of having these polyphenols glued to the fiber and how they can enhance their prebiotic effect. Still, some of these effects were donor-dependent, and I also showed the importance of understanding the compatibilization of any fiber when we want to, with the rest of the components, if we want to attain a successful integration of fibers into a product such as a baked system. And with this, I wanted to thank the main funding body, which is Independent Research Fund Denmark, obviously to my research team, to Clarissa that is here with us, Ivan, Pablo, Maria, Guillermo, Natalia, and Casper. Just one slide of propaganda. This is where we are at now. You are very welcome to visit us if you are interested in talking to us, in understanding a little bit food systems. We are open to any conversation. We have just launched the website. It's not fully completed, but you can access to it and you can see some of the things that we do and some of the services that we offer. And with that, I just wanted to thank you all for listening.
Yes. Hello, Michael. That's for you. That's for you. Well, in English, so I hope you listen to me.
All good.
Okay, then you say that the carbon footprint of the oils you are using is far lower than the one of palm. Which kind of, you mentioned coconut oil, which it's only coconut or other oils you are using, rapeseed or whatever?
No, for the palm alternative emulsifiers, we use only rapeseed and sunflower. So the coconut oil, in this case, it's only being used for the aerating and powdered aerating emulsifiers for cream applications.
Okay, then is it possible to use, I have only seen the problem in the cream application. You know, the rest is more or less working reasonably good. In this case, is there any possibility to use any other alternative with a lower footprint that gives better results because of the melting point?
Unfortunately, this is difficult. We also need to consider the amount of oils which are present on the market and which are available, and also delivers the technical performances. And the next in order from palm kernel would be coconut oil, and also from an availability point of view. There are certain, for sure, also other fats or oils which might be possible, but we also need to consider the amount of costs of the product at the end.
Thank you.
Hola, es para Regina. Una pregunta. Muchas líneas de producción de panes, como sabes, se emplea harina encima del pan para hacer el efecto rústico y precisamente es lo que hay bastante demanda. ¿Vuestra harina hace el mismo efecto? ¿Cómo actuaría en un pan? Porque claro, lo que no pueden hacer las empresas es cambiar de una harina a otra solamente para esto.
Correcto. Muchas gracias por la pregunta. Una de las otras aplicaciones que hoy queremos centralizar más como harina de espolvoreo, pero se pueden utilizar también como harina de decoración más artesanal. Una harina convencional capta el agua muy fácilmente a comparación de una harina termotratada. Por lo tanto, si estamos hablando de un pan que requiere una cierta congelación, puede ser que al ser descongelada cree como se cuartee la superficie. Por lo tanto, con una harina termotratada es mucho más fácil de evitar que penetre esta agua o la humedad de la cámara de congelación. Por lo tanto, obtenemos un producto con una superficie mucho más homogénea. Y además tiene ciertos beneficios que se enganchan mucho más fácilmente en la superficie. Por lo tanto, si su producto pasa por un envase, también al final crea el producto envasado, un envase mucho más limpio a comparación de una harina convencional, que pueden haber problemas de que no se cierren las bolsas de envasado o problemas de sellado por la turbulencia que hay. Por lo tanto, también podemos ofreceros beneficios por este aspecto. Gracias.
Thanks a lot. I have a question to Mario. First, thanks for the presentation and showing us how complex food systems are and how many interactions there could be. But it's more technical questions. So the deep eutectic solvents, they're really hot topic right now, and they're used for many applications. And yes, they might save us from using some chemicals for the reactions, but then the solvents themselves are also chemicals. And now one of yours was urea and the other one was a chloride type of. So this is a chemical too, and we would, if we produce in big scale, we would end up with a lot of this. Is that not also a problem?
Yes, so on the one hand, that's a good question actually. On the one hand, we are the problem of consumer acceptance of these products is still not the greatest because there is still the use of chemistry there. And there will be some reluctancy from the consumers. So that problem, we didn't avoid that. But what we did avoid is the use of something that is environmental, not very environmentally friendly. So on the one hand, we solved one problem, but the other problem still persists. I have to say though that this type of resistance starch is the most effective one. So this is you can create mostly like sand granules that are super resistant to everything. They will not swell. They are very inert. So this is very good to incorporate in any product because they will do nothing. And sometimes for some products or ingredients or polymers, doing nothing is something that we really want. So they are the most effective ones. But there is the problem of, yes, we use some chemistry to fabricate them. We are now focusing or working on creating some alternatives without the use of, well, we will always use chemistry because everything is chemistry, but we are trying to use some materials that are present in the diet that act as catalysts. But it's a very good point. There is still some challenges regarding that.
Thanks.
Thank you.
Hello, Evelina Hesch from Piratos. Thank you all three for the presentations, very interesting. I have a question for Michael, also as well related to the CO2 footprint. So thank you for mentioning the organization you use, so Carbon Clouds. Just when you compare the palm alternatives with the palm, do we speak then with a comparison of standard palm? or do we speak as well on a comparison with RSPO segregated palm?
Basically, we use only segregated palm oil.
Okay, so that 50% would be in a comparison with that. Okay. And do you see big differences when using then more the sunflower oil or the rapeseed based oil, or this is in the same order of magnitude as well?
This is in the same order of magnitude based on the fact that the fatty acid chain distribution is rather identical.
Yeah, thank you.
Also thank you from my side for the good presentations. A question for Mario. It's very interesting the depth you've gone into understanding the different constituents in apple pomace that provide this health benefit to consumers, and I think you've done something similar with psyllium. Is there any benefit in using those fibers as opposed to like wheat fiber? Could you comment on that? Is there is wheat fiber lacking some of these constituents so that we can actually get enhanced health benefits?
Yeah, thank you for the question. There is some in terms of the plant cell wall. The plant cell wall from cereals is mostly cellulose, but also in this case, as opposed to apple or fruits or some vegetables, it contains beta-glucan and arabinoxylans. They are still pretty good, and there is of course a plethora of metabolic benefits attributed to that. So I don't have an answer about what is better, if including some dietary fibers from cereals or from fruits, but they are compositionally different. In the case of the apple pomace, in this case we will have pectins and xyloglucans. What we know is that they have a very broad array of glycosidic bonds. So then it will be quite beneficial in terms of getting coherent responses across individuals. But that doesn't mean that the cereal fibers will not have that effect. They may also have that effect, and in fact, arabinoxylans are also quite of an interesting fiber to include to add into a product. I would say that perhaps one of the benefits and the reason why we focus on apple, it was a very distinct polyphenol profile that this is not present in the cereal, not as broad. So in the cereals, we can expect that we will not have this very rich content of flavonols, for example, flavanols, deoxychalcones. We will not have that in the cereal. So this is one of the reasons why we focus on the apple, and also because of the problem of the apple waste. Because we wanted to, this one of our ultimate aims is to, well, can we really use it? Can we really upcycle it into a prebiotic ingredient? So this is why we focus on apple. So I think it's interesting also because it brings the good things from the fiber, but also the good things of having polyphenols glued to it, and also the abundance, that it will be nice to try to do something with it.
Thank you.
Thank you for your very interesting presentations, all of the three of you. And I have a follow-up question for Mario as well. It was more about, it was very interesting to see this upcycling of pomace. Just wanted to know, when you did your baking trials, did you also study the impact on taste of these very rich polyphenols fractions? Do you have tasted? Do you know what would be the impact on taste? And the same way for the resistant starch, have you seen any impact on the texture, on the properties, on the taste of the bread that you have produced with these compounds?
Mm-hmm. Yeah, thank you for the question. So for the first question, did we taste it? I haven't tasted it. My students did, and it was still okay. You can still notice some of the differences, but it's not terribly worse. When we have created some things that are unpalatable, like some things that are no, this wasn't the case. It was still okay, but the texture wasn't correct. The texture was bad. was very the cohesive of the crumb wasn't good, not much resiliency. It was much harder. This is happening because it is like a bully in the schools. It steals all the water from all the polymers. It is, as with any other insoluble fiber that we add into a recipe, it doesn't work. It doesn't work nicely. In terms of the digestibility of the starch, we have an upcoming research study we're about to submit to see what happens with the starch digestibility, if these fibers will affect that. And it does beneficially, so the starch digestion rate and extension is decreased significantly, not dramatically, but statistically significantly, and we're expecting to be able to show those results shortly. But this could be also another beneficial effect of adding this type of fibers on, because it slows down starch digestibility, which is a well-known problem in bread systems. Thank you.
Mientras pensáis alguna pregunta más, porque tenemos tiempo, nos quedan aún casi 15 minutos de preguntas. Una pregunta para Regina. ¿Qué equipos tenéis para medir el polvo en las pruebas que hacéis?
Recomendamos ciertos equipos. Hay equipos más ópticos, hay otros que son con filtros que pueden ayudaros a analizar las distintas granulometrías que podéis encontrar suspendidas en el aire cerca de vuestra línea de producción. La recomendación que tenemos oficial de la BGN, la entidad alemana, es que lo mejor es tener una máquina que esté con el operario durante todo su proceso podrían ser las 8 horas laborales o el tiempo que esté expuesto, para realmente poder ofrecer unos datos reales del impacto o del riesgo que esté el operario. Por esa razón, según entidades pueden escoger distintas maquinarias. Nosotros tenemos una de ejemplo en nuestro stand de Disproquima. Si queréis venir, os la podemos enseñar cómo funciona. No es algo que vendamos, sino son como recomendaciones que os podemos dar si estáis preocupados o queréis mejorar la situación actual. Gracias.
¿Alguna pregunta más por parte del público? Si no, seguimos nosotros, o sea, no sufráis. Bueno, ahora, Mario, te quiero hacer yo una pregunta, porque luego tenemos que hablar mucho, que yo he trabajado mucho con fibra de frutas.
Ya me imagino.
Y si hay una cosa que tú ya lo has mencionado, pero me gustaría que nos desarrollas un poco más, porque no todas las fibras son iguales. Aunque la gente piensa que son unos ingredientes más que todo el mundo la conoce, pero no la conoce del todo. Porque todo el mundo quiere fibra, pero no todas las fibras sirven para lo mismo. Y realmente el mejor estudio es in vivo, está claro, pero ¿qué estudio in vitro recomendarías para que algo realmente salido de un laboratorio pudiera tener muchas posibilidades de ser una fibra buena para ser prebiótica, generar mejores probióticos, etcétera?
Hombre, yo creo que algo relativamente sencillo es utilizar un ensayo in vitro con inóculo humano y medir las cinéticas de fermentación, ver si se genera algún ácido graso de cadena corta y ver qué pasa con las dinámicas de las bacterias usando ensayos sencillos de metagenómica, que ahora no son tampoco tan caros de realizar. Yo creo que eso proporciona verdaderamente una buena imagen de lo que sería una fibra. No hay problema en dedicarle un poquito más de tiempo o en conseguir algún donor añadido. Sí que es interesante, en vez de utilizar lo que se llaman las pools, de coger, digamos, las deposiciones de varios individuos, luego juntarlas todas, mezclarlas y utilizarla como un inóculo común, sería interesante utilizar las de cada persona individual, porque así es como luego se ve verdaderamente el efecto, porque a veces, como tienen una baseline de microbiota tan diferente, al final los efectos podrían llegar a no verse. Entonces eso podría ser una recomendación. Otra recomendación también podría ser, pero aquí no con todas las fibras, sino con algunas, es, en algunos casos no hace falta, se puede utilizar la fibra directamente y conducir el estudio de fermentación in vitro, pero otras veces quizás la parte de la digestión podría ser clave. y no se podría obviar. Esto sobre todo cuando tenemos fibras, sobre todo relacionadas con almidón resistente, de cualquiera de los tipos, porque podría afectar, el proceso digestivo podría afectar la fibra. Es decir, un almidón resistente, por ejemplo, un tipo 1, un tipo 2, que no se haga no se simule la digestión, podría tener un efecto probiótico muy interesante, pero eso no va a pasar en la realidad porque va a ser digerido. Entonces, podría ser interesante acoplar estos dos mecanismos para sacar información. Pero yo creo que así puede ser información bastante útil. Uno de los problemas es la falta de estandarización, diría yo. Pero yo creo que estamos todos trabajando en ello para poder hablar un idioma común cuando obtenemos cosas en el laboratorio in vitro.
Y déjame una derivada de la pregunta, porque, muchos polifenoles también son semioquímicos, también sirven como pesticidas naturales, para que nos entendamos. Y lo mismo, no todos los polifenoles son iguales, eso también lo sabemos todos. ¿Cómo sabes si puedes tener un problema si un polifenol que sobre el papel entre y se te cargue la medio microbioma porque seguramente no pueden resistirlo? ¿Eso lo podemos saber antes de hacer un estudio más bien hecho?
Es un tema complicado, y es muy buena pregunta, además. De hecho, cuando condujimos este estudio de los polifenoles y queríamos ver un poquito el efecto probiótico, no solo es el efecto probiótico, es que igual era el efecto contrario. Igual precisamente podría llegar a destruir alguno de las especies o de las familias que son beneficiosas, y a veces pasa. Entonces, de hecho, queremos un poquito estudiar un poco más. Fue complicado porque en el estudio metabolómico detectamos 25.000 compuestos. El análisis de estos datos es un poquito complicado. Nos centramos simplemente en estos para un poquito que nos diera información de su metabolismo, primero ver si se metaboliza o no, y segundo ver si un poquito se alinea con la producción de ácidos grasos de cadena corta, pero aquí hay mucha tela por cortar. Es un tema complicado.
¿Alguna pregunta del público? Pues voy a preguntar a Michael one question regarding you have talked that based on the information that you have provided in bread, it's easy to change from palm to non-palm. In the sponge cake, it seems to achieve the same butter density. You can also have good results with both options. But what happened with the texture aspect of the product? There are any difference on that?
No, actually there are no differences. Both products behave absolutely the same in terms of formation of the foam, as well as then later on the crumb structure formation. Surface is also identical, I would say. So you can replace one by one. In this case was the answer.
I'm following with the sponge cake. When you change from palm to non-palm in the label, there are any changes? You are using different emulsifiers comparing to the palm base, to have the same performance?
That is actually a good question, because of the same counts here as well for the fine bakery emulsifiers, that the impact of the temperature of the melting range also impacts the volume generation during the mixing process. And therefore, that was a task of for R&D to come to the similar result. And therefore, they need to apply also different kind of emulsifiers in terms of the labeling. Yes, there is a slightly change in the label to make those kind of product more hydrophilic, to bring the more lipophilic or the more, let's say, the higher melting emulsifiers into solubilization, into distribution, therefore, that they can generate the volume and the crumb structure.
Ya tenemos 5 minutos para preguntas. ¿Alguien más se anima? Venga, va, que es complicado tener estas personas para que os respondan lo que queráis, ¿eh? Si no...
Quizás una pregunta para Regina. ¿Puedes decirnos qué diferencias hay entre el tip top y, por ejemplo, harinas de arroz o otras alternativas que pueda haber en el mercado?
Tenemos clientes que utilizan, no porque nos hemos focalizado solo con la harina de trigo nativa, pero hay otros productos que se pueden utilizar, como la harina de arroz, como has mencionado correctamente, aunque continúa siendo un producto con elevada polvorulencia y además, si está molida muy fina o hasta granulometrías más grandes, el producto final queda un poco más sucio en la superficie que está en contacto con la placa de cocción. En ese caso, con Tip Top puedes obtener un producto de elevada calidad, ya que se engancha menos en la base del pan y genera un producto mucho más limpio y visualmente más agradable, ya que son productos que al final terminan siendo expuestos dentro de un envase y el envase también queda mucho más limpio. Gracias.
¿Alguien se atreve? ¿No? Pues vamos a pasar ya a clausurar la sesión. Os vamos a recordar, por si acaso, la dinámica de esta tarde de los talleres, de los workshops. Recordad que son 2 salas que están en la tercera planta, ¿no? En la sala N2, que está marcada como color rojo, como el circulito que tenéis en la identificación, y que es la sala español, porque es la que no va a haber traducción y se hará en español todo, recordarlo. Y luego está la sala N3, que es la sala verde, con el verde, y que ahí sí que habrá una traducción, es la sala inglés. Y habrá traducción del inglés al castellano y viceversa. Eso sí, recordad que tanto los talleres de Anton Par, que no se celebrarán en ninguna de las dos, sino en la 419, por un tema logístico del equipo que tienen que utilizar, y que realmente empieza la primera sesión de una de las salas es allí y la última sesión de la otra es allí, ¿vale? Manteniendo el tema de la traducción. Y los que tenéis el símbolo azul es que estáis en lista de espera. Una vez ya se hayan llenado con la gente que esté, pues ya se irá, ya podéis entrar si veis que hay sitio. ¿De acuerdo?
15:30 en las salas de la planta tercera. A las 15:30 tenemos que estar allí, con lo cual con un poco de tiempo para poder llegar. Pues buen provecho.
Buen provecho. Recordad, no os quedéis solamente en la sala cúpula, sino ir saliendo al hall cuando ya tengáis la comida. Llenemos un poquito el espacio, que estemos más cómodos todos. Y recordad que hay una exposición de pósters en la entrada que también es muy interesante, que tenéis que ir a ver.